Hi everyone and welcome to video number 15 of this series in which we are learning how to model an end plate steel connection, which is this model that you see here. We are now working on the second version of this model in which we are modeling the bolted connection using solid elements. So if I activate the visualization of nodes, you see that for the bolt, we are using second order tetrahedrons with the mid-side nodes and the curved sides. For the washer and nut, we are using first order hexahedrons with only corner nodes and straight sides. And for the axis, we are using incompatible modes formulation. Let me deactivate visualization of node. And now in this video, we are going to work on the connection between the nut and the bolt, which is performed by using a translator connector. And we're going to also use this translator connector to apply bolt pretension. I have a blog article that I teach about two ways to apply bolt pretension. One is the one that we are going to use here by using a translator connector. And the other one is by using a bolt pretension section. But in this tutorial in my blog, I use Abaqus CAE application to teach about it, which is the application that we have used for simpler models. In this video, we're going to learn how to do this using ANSA. Okay, so first of all, just to be sure that you have the same visualization setup as I have, choose Abaqus deck here, and in the database we can deactivate visualization of curve and point, and in the pink buttons you should have everything that I have activated here, and also for the yellow buttons in here deactivate the spots and hard points, and in the draw mode select property ID, and that's it. Now before we start modeling this connection, let me just make a comment about the threads of the bolt and the nut. Obviously that we haven't represented the threads here in the bolt and in the nut. It's not feasible to represent the threads in details in large models, and it's not needed as well. You know that the threads are very small features, and then if we represent it here, we would have very small elements in this region. The mesh would be very complex, and this would bring a huge computational cost to this analysis. So when we are using commercial items, so when we use a bolt that we have chosen from a catalog and a washer and a nut chosen from a catalog, we don't need to validate the threaded region of the bolt and nut, because it has been validated previously already. The only thing that we need to validate in an FEA model is these. Let me isolate the bolts and get this view. Imagine that you don't need to do what I'm going to do here. Okay, imagine that we have the threaded region until here. Then we only need to validate the bolts in the region between the thread and the bolt head. So we would need to validate only this region of the bolt, okay, without the threaded region, only this region here, because this is for commercial bolts. The threaded region is validated in a way that it is stronger than this region that we need to validate, okay? And also the same is true for the bolt head. Now, if you're not using commercial bolts, then we would need to validate the threaded region, but not in a complex model like this one. We would have to create a model with only one bolt and with the thread represented, very small element. And then we would have to validate the threaded region in a way that it is stronger than the this region here of the bolt. I guess it's named as chink or shink, I don't know. Okay, because if we validate the threaded region in a way that it is stronger than this region here, then we can use this bolt in a larger model without representing the threaded region. And then we would need to just validate this region here that is weaker than the threaded region. Okay, so that's the idea. And this same rationale applies to the bolt head. Okay. All right. And for the net, we don't need to validate the net as well, because if it's from a catalog, because it has been already validated. Okay, so in the catalog, we would have the information about the maximum bolt pretension that we can apply with this net. And then we are going to respect this limit. Okay, so in this model, this net is only used, well, it's important to have the net with the real geometry here, because it's going to, if we have the correct geometry, it's going to represent the stiffness in this region correctly, even though I don't want to analyze the stress in the net. And it's also going to represent well the contact region between the net and this red plate. Okay. Okay, so the net, the washer, we don't validate. We only validate this region here of the bolt. Okay, in a nutshell, that's it. Okay, so let's start creating this bolted connection between the net and bolt. Let's use the not function. And I'm going to select here property ID selection mode. And then I'm going to position the mouse here on the net. And then you see that since we have the net and washer with the same property, if I try to isolate the net in this way, I'm going to end up selecting the washer as well. So there is a specific tool here in the selection mode named property ID region. This one works like this. If I position my mouse on an element, it's going to select all neighboring elements that are part of the same property. But it's not going to select elements that are part of the same property that are not neighbor elements, such as these ones. Okay, so this is a very useful tool. I use it a lot, and it's important to understand and use it as well. So select the net, middle mouse button again, and now we have the net isolated. First of all, we need to create a coupling with the nodes that are part of this internal face where we would have the threads. So select Abaqus deck and search for the constraints group, left click on coupling, select nodes, and then in here, let's activate the selection mode here to select surfaces or solid faces in this situation. Apply feature angle or feature area, it could be 40 degrees. Select, oh, it has selected everything. So let me use the right mouse button to deselect and select only this internal face. I don't know why it's selecting everything like that. Let me deselect everything. Let's try another tool. Let's use here macro area. It's not working as well. Let's use feature area, but let's decrease here to 20 degrees. I guess this is a visual bug. Let's try to click with middle mouse button. Yes, this is a visual bug actually. It's only selecting this internal face, but it's showing like it's selecting everything. So we have 80 nodes selected. Next. And now for the control node or the reference node, it's going to create automatically on the convex hull centroid. That is on the COG, not COG because these nodes doesn't have don't have mass, but it's on the geometric center. We have this other option here, average position. I guess the result is very similar. Let's choose convex hull centroid. Click on next, and then this is very important. We should choose kinematic coupling. It's not possible to use distributing coupling here because we are going to have instabilities occurring when we apply bolt pretension. Okay, you can try to use distributing and you're going to see that your model is not going to converge. So we're going to use kinematic, and in parts we can select ask always and finish. And then in here we need to select the part. It could be auxiliary entities, and that's it. Now we have the coupling. Now imagine the following. We are going to have the translator connector defined in a way that one of its nodes is going to be this node here. So the bolt pretension that we're going to apply is going to come from this node, and it's going to be distributed among these nodes here in this internal phase, which is what should happen, because what applies the bolt pretension in the bolt is the threads that we have in this internal phase. And that's why I like to use this methodology to apply bolt pretension, because the force comes from the correct place. Now, now that this is ready, I'm going to click in show all, and I'm going to isolate, let's use the not function, and then I'm going to select by property ID region, select the bolts and also the nut. Middle mouse button again, and then press ask, and I want to create a coupling in the bolt, considering only the nodes in the outer surface of the bolt in the region that we have the thread. Okay. So that's why I have the nut visible here. Let's press F1 to get this view. And then let me use the lock view and then the not function. And then I'm going to select the nut, and let's try to analyze what rows of elements we should consider here in the creation of this coupling. So I'm going to hide this nut, and looks like we need to use maybe these 3 rows of elements, this one, and this one, right? If I click in show all, yeah, I guess this is a good idea, because you should imagine that when we have bolt pretension, the nut is going to move to the left, right? And then it's going to, so we can imagine that we have some threads here in this region here as well, right? Where the nut is not occupying yet. But the nut is going to move to the left, and then we should have some threads here. In your case, you probably have a mesh that looks a little different, right? So you should perform an analysis like this in your case to define where you should have this coupling defined. So let's select, let's go to Abaqus deck. Let's create a coupling here again, nodes. And then to perform this selection, what we're going to do is the following. Let's activate this option that is already activated in my case, feature area. And here we have 20 degrees now, and then you see that it's only selecting this fillet. I'm going to increase this to maybe 50, and now it's selecting all this surface, but I don't want to have all these selected. I want to deselect this first row, and I want to I used the right mouse button to do that. And then I'm going to use the right mouse button to create a box selection to deselect until here. Now I have only these 3 rows of elements selected. Middle mouse button, and then it's going to select all these nodes. Notice I have only the nodes in the outer surface of this bolt selected, which is where I imagine that we have the thread. We don't have the internal nodes selected because the force is not applied on internal nodes. The force is applied on external nodes where we have the thread. Okay, so this is important. I see that sometimes people create a selection like creating a box selection like these in this region, but if we do that, you're going to end up selecting internal nodes. Click on next. And then the control node is going to be automatically created on the geometric center, calculated automatically. Click on next. And then this should be a kinematic coupling. This is important. So choose kinematic, ask always, finish, select auxiliary entities part, and close. Okay, now let's click, let's deactivate. Actually, we can have this lock activated because if I click in show all, it's going to show the net. There is, let me double click here in constraint, and I'm going to create a box selection like this. And then you see that when I do this, I have in this list of couplings only one selected. But I wanted to have the coupling of the net visible as well. There is a very important tool that I have used previously, but we're going to use it again. And let me explain about it again because it's very, very important. It helps a lot. This tool here, neighbor, brings visible all connected entities to the already visible ones. If I left click and hold, we have 2 options, first level or all level. To understand this, let me isolate using the not function, entity selection mode. I'm going to isolate one single element, this one, middle mouse button. You see, I have only one element visible, right? Now, if I use left mouse button and hold and first level, it's going to bring visible all elements that are connected to the element that was visible. And then if I click here again, this happens, and so on. Okay, so this is a very useful tool. Now click in show all, and then we have these entities that are in the lock view that we have activated. And if I want to have the coupling connected to this net visible, I should click here in neighbor. And then since the coupling is connected to the net, it's going to make this coupling visible. We also have here some springs visible that are connected to the bolt. Now double click on constraints, create a box selection, and then you see that now we have 2 selected. So we have the 2 couplings visible. Okay, what I'm going to do is, now that I have these 2 selected, right click and show only. Now we have the 2 couplings visible. Press ESC to deselect these couplings. And then you see that it's hard to tell which coupling is connected to the net and which one is connected to the bolt, right? But you see that we have a node here positioned here, one reference node positioned here, and the other reference node positioned here. These are the nodes that we're going to use to create the translator connector. And we should follow some rules and good practices. First of all, the connector load is going to be applied to this net, right? One thing that I want to guarantee is that these nodes are passing through the center, the axis of the bolt. in this case, since we have used these nodes to create the couplings, and then the reference node was created on the COG of these nodes, then this is already passing through the axis. But sometimes the nodes that we selected are not part of so perfect surfaces. So it's important to guarantee that it's passing through the axis. I'm going to use a tool here to make sure that this is happening, even though in this case we don't need. But I'm going to show just to teach you in case you have to deal with a situation that you don't have a perfect surface to create the coupling. Okay, so I'm going to unlock and lock again so that I have these two couplings visible. And then I'm going to use these two couplings as the lock view, and then I'm going to use the invert tool. So it's going to show everything that was not visible, and it's going to hide everything that was visible. And then I want to create 2 points that passes through the axis of this bolt. I'm going to do this by going to the classic topo module, and then I'm going to use inside points group. I'm going to use this tool here on COG and circle. And also I'm going to activate the visualization of points here. And then the first point is going to be on the center of this first circle. So select this node, and this node for example. You just need to select 3 nodes that are part of this first circle, and then press middle mouse button, and there we have the first point. The second point could be here. Let me use the not function, property ID selection mode, hide the washer and nut, deactivate not function by clicking here. Now you see that I have the COG circle activated. Select this node, rotate, this node, and then rotate like this, and then this node. Middle mouse button, and then the point was created there, and we cannot see it. Now let's click in show all so that we have everything that was in this lock view visible now, which are these 2 couplings. And in my case, I have these 2 points as well. If you don't have this visible, just in the database, right click on points and click on show. Okay. Now I'm going to use a tool that we can find in the classic mesh module, and then it is the align tool. I don't even remember where it's positioned because I use it's here. I use a shortcut for it, Control A. You probably don't have this shortcut activated because you need to set up here in tools. So let's use the inside grids group. Let's use the align tool, align. And then the nodes that we want to align, the source nodes, we should zoom in here. And then it is this node and this node, the 2 reference nodes of the couplings. Zoom out, next or middle mouse button. And then I want to align by selecting this point and this point. And then it creates this axis, which is the bolt axis. And then let's zoom in here just to see. You see, these points are already passing through the axis, so we would not need to do this, but in case you need, this is how you do this. If we click on next, yeah, you see we had some movement, a little movement here, and then finish. Okay, so this is a good practice to guarantee that this is going to work properly and without any convergence issues. Now, another thing that I wanted to do is to create the coordinate system that is going to be used in this connection. We need a coordinate system for the translator. So let's go to the Abaqus deck, and then let's, in the coordinate system group, coordinate, left click and hold, rectangular, and then select this point here and this point here. Middle mouse button, or actually, let me just close this. And then in the database, I guess it has created this coordinate system. Where is it? I lost it. Well, anyways, maybe it didn't create actually. Okay, so we can create this coordinate system by selecting these 2 points. It's okay. But I actually want to create it by selecting these 2 points to define the x-axis. It's going to result in the same. The result is going to be the same, but the origin of the coordinate system is going to be different. I'm going to do this just so that we have the origin, for example, here. So coordinate system, rectangular, and then zoom in, select this point as the first one, which is going to be the origin. And the second point is to define the direction of the z-axis. And we know that we actually want this to be the direction of the x-axis. So we will need to rotate this coordinate system. Middle mouse button. And then in here, let's say that this is the translator coordinate system. And then, as I have explained in details previously, when we created the coupling for the beam element in some videos ago, we need to perform a rotation about the y-axis by minus 90 degrees. Okay, let's click on OK. And now if I zoom in, I have the x-axis in the correct direction, which is going to be the only degree of freedom of the translator connector, as we know. Okay. All right. Now let's press ESC. And now we need to understand if this reference node is part of the coupling connected to the nut or the washer. So let's see. How can we do that? One way is to hide the coupling that has this reference node by using the not function, entity selection mode, and then select this coupling here that has this reference node. Now it's not visible anymore. Press ESC. Now, if we use that tool neighbor first level, it's going to make the elements that are connected to this coupling visible. And we can see here that these are the elements that are part of the bolt, right? So now we know that, let me click in show all. Now we know that this node is part of the bolt and this one is part of the nut. If we create the translator from here to here, and by having this coordinate system in this manner, then if we apply a bolt pretension, let me press F1. If we apply, let's create these connectors so you're going to understand better this explanation. In the Abaqus deck, inside elements group, use this tool here, 2 nodes, and then select this node as the first one and this node as the second one. Middle mouse button, and then we can put it, let me see, connection entities, yeah, connection entities part, for example. And then we need to create a property for these, so right click, new, this is the translator connector. And then in component 1, search for T, translator. And then in orient 1, the coordinate system of the first node, question mark, and select this coordinate system that we have just created. And then we don't need to define an MID. Click on OK. And then select this property. And here we have the connector card with the ID of the connector, property, node 1 and node 2 ID. Click on OK. And here we have the translator created. And so let's continue that explanation. Let me press F1 to get this view. So we have, let me take a screenshot. This is very important. And this is something that I got really confused at first when I started working with this type of connection. What I'm going to teach here is something that is applicable for all kinds of connectors, not only this one. So here's the situation that we have, right? And this node here is connected to the bolt. This node here is connected to the nut. I never know if nut has two T's or only one. Second important information is that the x-axis of this coordinate system is from this node, the bolt node, to the nut bolt. So the x-axis is like this, right? So we have the x-axis oriented in a way that, and by the way, guys, another thing that is important is that when we created this translator, we have firstly selected this node and then this node. So the bolt node is the first node in the definition of this translator, and the nut bolt is the second node. This information is important because we have this coordinate system in a way that it goes from the first node of the translator to the second node of the translator. Okay, if we have this condition, if we apply in this connector load a positive connector load, so if we apply in this translator a positive connector load, then the nodes of the translator are going to move. This one is going to move to the left, and this one is going to move to the right. Okay? But this is not what we want, right? Because what we want is that the nut to move in this direction and to the bolt to move in this direction, right? Because if the nut moves in this direction, let me go back here and use the neighbor function. I want this nut to move to the left, obviously, right? Because if it moves to the right, it's going to be removed from the bolt. That's not what I want. So in this case, then I need to apply a negative connector load. If I apply a negative connector load, then I'm going to have this node moving to the left and this one moving to the right. The software is going to move these nodes until the reaction force produced by this movement is equal to the connector load. Okay, and this reaction force is going to come from the contact that we are going to have between the net and the column flange. Okay, now another thing here is that imagine that instead of defining this coordinate system like this, I have defined this coordinate system. Let me erase this. I have defined this coordinate system in a way that the x-axis is going from node 2 to node 1, to the second node in the definition of the translator, to the first node in the definition of the translator. In this case, the rule is going to be the opposite. If I apply a positive connector load, then the nodes are going to try to move in this direction. So it's going to be the opposite. Okay, so that's why this is a little confusing. So what I usually do is to always define the x-axis from node 1 to node 2, so that I know that if I apply a positive connector load, I'm going to try to perform this kind of movement. So what I'm going to actually need to do is to apply a negative connector load. Or another thing that I do and that I teach in this article is to move. This is another technique that is important, which is to move the node of the nut in a way that it's going to be positioned behind the node of the bolt. So that when we apply a positive connector load, this node is going to try to move in this direction, and this one is going to try to move in this direction. So this is another way we can do this. Okay, so there are many ways we can do this. Okay, so let me click in show all. So I have the couplings here and also the translator. If you don't have this translator visible when you click in show all, you can right click here in connector and show. And another thing that I also do sometimes is to, this distance between these nodes. Sometimes I just make this distance to be smaller, but it's not really needed in this case. Okay, it's just really needed if we have a too large difference. In here we can just, well, I guess we have a good distance here. We can just accept this distance here. We can even measure these using the measure tool. From here to here, we have, let's select nodes from here to here. We have 1.5 millimeters, which is a good distance. Guys, let's deactivate this lock view, click in show all, and let's let me see how much time we have here. We can now apply the bolt pretension. So since I know that I'm going to have, well, actually, before applying the bolt pretension, let's copy these to the other holes. Yeah, let's do this. It's going to be easy. To do this, firstly, we need to have some reference points to be used. My idea is to copy in a way that we are going to, let me adjust one thing here. So we are going to copy in a way that we are going to translate all these entities to these other positions. So I need to create some points for this translation. First of all, use the not function, property ID selection mode, hide the bolt, the washer, and also here inside elements group, right click in spring and hide, and also in constraint, right click and hide. Okay, you should have points in here. In points, let's delete these points that we have created so far, because we're going to create some new ones. And then go to classic topo module, and then again use the onCog circle tool, and then select 3 points from this circle, middle mouse button. Here we have the first reference point, and let's do the same thing for all these circles. So here we have the second. Just be careful so that you correctly select the nodes. Well, after this copy, this model is going to look really nice. And after this copy, we just need to work on the connector load and contact definition. So we will be almost finished. All right, now let's click in show all and press ask. Now we should be really careful in this copy procedure. This is another thing that I struggled a lot in the beginning when I started working on ANSA. I'm going to use the not function, property ID selection mode, select this bolt, this washer, middle mouse button, and then you see that we have some missing entities that I also want to include in the copy tool. And then to bring visible everything that is connected to these entities, let's use the neighbor function, left click and hold, and then click in all. So it shows everything that is connected in one click. You see that it doesn't show other parts, even though we have contact defined between the nuts and other parts, because it doesn't consider contact as this kind of contact. This kind of connection in this tool. Okay, it doesn't consider contact. Okay, now that I have the, and also in the database, make sure that you have a spring activated, and also connector activated, and constraint activated as well. Because I want to copy the sorted elements, spring elements, the couplings here, and the translator. Okay, now that we are sure about it, we can use the transform tool, copy, and then in the selection window, I want to select entities, select everything here, creating a box selection. And then after that, just to guarantee that I'm going to select everything in here, I'm going to also select here nodes and create a box selection. So it selects every node that is visible here. Okay. Middle mouse button. And then I have the copy mode activated. And then I want to translate. Now, let's use the invert tool so that we bring everything that was not visible visible, and everything that was visible we hide. And in this translator, in this translator tool, I want to, let's do one thing here. In this auto paste geometry, let's just click in no. And then in this translator tool, you should have translate tab here. Select this as the first node, and this is the second node. And then click on apply. And now this part is really important. For property, we can select here, for example, if we select auto offset, then it's going to create different properties for these new entities, but that's not what I want. I want this option here, no offset, so that these new entities are going to be part of the same properties. For parts, we can also select same part. I don't want to create new parts for these new entities. And then for set, since we have contact here, and for this contact, we have some sets of surfaces, I'm going to click on expand. Or actually copy, because I want, instead of expanding the existing set, I want to create another set that is going to be composed of the same elements. You're going to understand after we perform this copy. Click on OK. And now we have there the bolt. Why don't I have the nut visible? Let me check one thing here. Click on finish. And now click on show all. Oh, okay. Now we have the nut here. Okay, so you see that in this copy, let me use the nut function, property ID. This bolt, this new bolt, is part of the same property of the other bolt. And this is true for the washer and nut. Okay, so that's the meaning of that option, no offset. Let's analyze the sets and the contact. Here in contact, expand, double click on contact pair. Let's increase the size of these, and let's see these contacts. We have these contacts here, and then you see that it has always it has also created some additional contacts here. But we need to work on these two contacts because we have only the master surface selected for these two contacts. Okay. So let's do this, but before, let's firstly create the copy of these bolts for all the other holes. So let's do this. Again, we will need to use the not function property ID selection mode. Or actually, in this case, we will need to use the property region selection mode so that it only selects one bolt. This one, and this one. Mise mouse button again. Neighbor all. Copy. Entities. Select everything. Nodes. Select everything. Middle mouse button. Translate. Copy. Invert. From this point to this point. Plus no offset, same part, copy. Click on OK. And now you see that after copying, we have a new function activated, which is move, to move these new entities that we have here. So for example, if I wanted to create one additional move of 10 plus, then it's going to move these entities here, but that's not what I want. So I'm going to click on minus to return. And then what I want is to create another copy of these entities. And then let's hide the visibility of solid elements by unchecking this box here, volume. And also this box here, okay, for FEA entities. And then I want to create this copy from this point to this point. Plus, okay. And now if I have this visible and also this visible, you see that we have one new bolt here. Now we have the move tool again activated for these new bolts, but I want to actually copy and then deactivate these and these from this to this. You can use the middle mouse button and then OK. And if I activate it here, I have this copied to this position. Okay, so deactivate again. Copy from here to here, middle mouse button. Okay, and then copy from here to here, middle mouse button, and okay. And then copy again from here to here, middle mouse button, and okay. Let me check if we have all bolts. Yes. And then click on finish. Close and then show all. And now we have all bolts well positioned. Okay, so this is starting to look great. And now we just need to work on the contact and connector load. Let's firstly apply the connector load because it's easy. So first of all, I need to create a set, right click, new, and select connectors, select all connectors, middle mouse button, and then this is an element set. This has the translator for bolt pretension. You can give any name you want. The ID is 65. Click on OK. Close. Abaqus deck. And then in here, search for loads group. And then we have this one, connector load, set. Let's search for this last created set. Double click. And then in here, I want to apply this on the first step on this element set. First degree of freedom, and then the magnitude is 1 minus, we need to apply as negative bolt pretension, minus 155,000. Okay, here we have it in newtons. This is the bolt pretension, right, from that article. Click on OK. And then we know that, let's go to the step manager, open it. And then in the step manager, we know that in the second step, double click, we have the reset of the connector load, right? So we know that we're going to substitute this connector load by a connector motion. So we need to create this connector motion inside the boundary group, connector motion, set, search for the last set created here, translator bolt pretension, second step, and then I'm going to fix the first degree of freedom. Click on OK. And that's all. That's all we need to do for bolt pretension. You see that I was faster here. I didn't explain so many things because I have explained in details about everything that I have done here in a previous video. Okay. All right. Now let's work on the contact. And let me save this because we have done many things. And let's go to the contact pair. We have now 25 contacts. Let's go in the first one. And let's see. Well, this is all right. This is all right. And also this one is all right. Let's see this one. Looks like it's all right. And this one we have the master, which is this surface, but we need to have this slave. Guys, it's possible to create only one contact for this one. Instead of having very many contacts, one for each bolt, we can create one single contact between this face of all washers and the end plate. It's possible to do this. Okay, it works. But in this case, just to practice, let's do one contact per bolt. Okay. So let's do this. So in this contact, let me search for it. This one. Double click on it, and then you see that I have this slave surface with this color, which means that there is something wrong. So use the question mark, and then we have this set, right click and modify content. And then I want to select shell, and then feature area 50 degrees, and then select this area here. Middle mouse button, and then double click on these. And then let's change here the visualization mode to entities. We should have the negative side of this shell. Let's check if it's correct. So select here, press F2, and then in here we have the negative side. Click on OK, and then click on OK. Now, if we go to this, whoa, let me see one thing here. Well, for some reason, it didn't work. So let me double click here. Question mark. Oh, it has selected a different coupling. It was supposed to be the one with ID 3. Click on OK. Now it's correct. Okay, I have typed 4 there, so it became 34, and this set doesn't exist. Let's go to the next one. And then this one is between the nut and this back surface. So double click in this slave, question mark. Sometimes this happens. You see, when I use the question mark, I don't see anymore the set that was selected. So let me close, and then I have lost this information. Let me just cancel, and then double click here again. And then I need to use memorize that we have the set with ID 2, question mark. And then let's select this one, right mouse button, modify content, and then select this surface. There is no need to have all of these, so deselect this part here. Okay, so this looks okay. This looks okay. Middle mouse button, select this one. Press F2. We should have the positive side. It's okay. So click on OK, and that's it. Now we need to do this for the other contacts as well. Okay. So we should go one contact. We should go checking each contact. This one. Question mark on slave 28. Modify content. Select this surface. Deselect this part because it's not needed. Okay, middle mouse button, select it here, and then click on OK. Select this face, middle mouse button. We are almost finished. Yeah, you see, this is not so practical I usually create one contact and include all the surfaces. But in this manner, we can at least practice. Oh, I have selected too many elements. Let me deselect all these. Slave, question mark. Oh, I have lost it, but it was 43. Select these, deselect what is not needed. Okay. Now the last one. Okay. Guess that was the last one, or maybe not. Okay, this one is the last one. Okay, now we are finished. Let me see, 57 minutes. We probably have all contacts. Let me change here to property ID draw mode. We probably have all contacts defined. One last comment about contacts is that there is a chance of having contact between the bolt and the end plate in this hole, right? I'm talking about this contact that we can have between this outer surface of the bolt and this inner surface of the hole in the end plate, right? At first, I'm not going to define this contact, but if in the post-processing I notice that we have some penetration, then we would need to consider this contact. If we are interested in this stress, in this region where we have this penetration, okay? So we should analyze if we are interested or not. And let me tell you that we would have some convergence issues with this type of contact, and there are some tools, very important tools that we can use to facilitate this convergence. I'm not going to really explore about it in this tutorial, but if you'd like to know more, it is this one here, surface smoothing. This tool, if I left click and new, you see that we have this kind of surface smoothing for circumferential contact. We have also spherical contact and toroidal contact. Okay, so you can research about it if you're interested. Maybe in a future tutorial we can use this tool. Guys, I'm going to use the compress function, details, alt X, deactivate and activate. Let's scroll down. And let's click on OK. I know that there is one thing that we need to do here in material list. There is the bolt material, and this is standard steel. By the way, check this so that it's defined. and that so that it's going to be written in the .inp file. And I know that we need to redefine the bolt material, right? Because we have lost the previous definition. And I guess that's all. This model will be ready for us to run. I'm going to do this in the next video because there is actually two things that we need to do. This material setup, and there is also one thing that we're going to use here, which is a control, which is something that is new. We are going to use this tool here to apply a control that is very important for nonlinear analysis like this one. Okay, but I'm going to talk in details about it in the next video. And then we can run it and post-process the results. Maybe I will be able to do this all in one video. So maybe the next video is the last video of this tutorial. Okay, so I hope you are learning a lot by going through all these videos. I know that this is very tiring. I am tired of creating these videos, but I guess the effort is worth it, because what you're learning here is really valuable for you to apply in the real life. Okay? All right, so see you in the next video.